On the sidelines of the recently concluded AI summit in New Delhi, India also became a part of Pax Silica. Pax Silica is essentially a US led initiative to counter China's dominance in new age sectors such as semiconductor fabrication, artificial intelligence, fiber optics, and undersea cables, and critical mineral supply, among other things such as information, communication technology, and data centers. So these have become of late India's primary areas of concern, not only because of India's lack of hardware capabilities, but also India's scarcity in the materials or the minerals which go behind the fabrication of the materials used for this new age sectors. So our topic for today essentially will be this. This is an interesting topic because Pax Silica is more about hyperbole. Okay, we are going to form this found groupings like there are IPEF and Quad. We are going to con to China and we are going to do this and that. But where, what is new in that? Beyond the politics, beyond the strategy implementation, we are going to discuss something new. But Pax Silica, because it was in the news, and from the point of view of various international groupings, that is why we have to discuss it. So, first of all, I have given you the definition or the meaning of what Pax Silica denotes. So initially, India was left out of the Pax Silica initiative. Why? I've already given you the reasons. India lacks the hardware capabilities, the development capabilities, as well as the essential supply of critical minerals. What are critical minerals? We'll get to that in a moment. Now, initially, Pax Silica consisted of limited countries as part of its grouping. Now, why those countries were included? I'll tell you. They included Japan and South Korea because of its chip semiconductor dominance. They chose Australia because of its production of critical elements and lithium reserves, which is an important component of what our main topic focuses today. Also, lithium ion batteries, they have become the primary source of electric vehicles, and everything which was earlier managed by the nickel cadmium cells or the lead acid batteries, so they have replaced that. Okay, Israel and UK, why? Because of their innovation ecosystems. Why Netherlands? There are some new technologies. So Netherlands holds expertise in those. One such novel technology is lithography. Okay. So I read about this. What exactly is this? Because I normally I'm not inclined to just mention the name. Lithography, especially photolithography, which is important from the point of view of our discussion in terms of semiconductor fabrication. So it is a technique in which UV rays or UV light is used to draw circuit patterns. Okay, so it's a novel technology, circuit patterns, and that is how it helps in designing the semiconductor chips and other things related to electronic semiconductor fabrication. Okay, so this is why. So India lagged behind, but ultimately we all know India has shown enough talent, tech talent, and India is a means to diversify to various markets. So instead of just staying as a middleman between the countries which hold the reserves of minerals or elements like lithium and the Chinese processing dominance, India decided to take proactive part, and sign the Pax Silica initiative. Okay. Now, currently, where do we stand vis-a-vis China? Okay, so we are talking about the topic basically is lithium ion versus sodium ion. Very interesting. We'll just go for the facts first and the concepts we are going to discuss later. So recently what happens is, see, lithium, like I told you, first let us talk about this. What are exactly the rare earth element and critical minerals of which lithium is a part? Now, this is very important and interesting. So, critical minerals are a broad category of elements or minerals which are of strategic value and whose supply chains are vulnerable to shocks, whether be shortage of production, shortage of reserves, or volatility in markets. So these are the broad chain. So here, if you can see the gray and this turquoise colors, this gray, these all are critical minerals. Okay, so we have talked about lithium, beryllium. Okay, the important things: strontium, titanium, chromium, vanadium. So like titanium and vanadium are used in the metallurgy. Then cobalt, very important component of lithium ion cells. Then gallium, germanium, okay, osmium, hafnium, tantalum, tungsten, cesium. Okay, so all these are critical minerals, a larger umbrella term. What are rare earth elements? They are not rare in nature per se. Rare earth elements, they are a subset of critical minerals which are concentrated in a few pockets of the world. Okay, so that is why they are rare. They are not rare by occurrence, they are concentrated in a few geographical areas of the world. So, primarily, there are 17 rare earth elements which, so we can say that all rare earth elements are critical minerals, but all critical minerals are not rare earth elements. Okay, so basically you need to remember this just for information point of view. So we have this, if you remember the 10th 9th 10th periodic table chemistry, so this entire periodic, this F block, okay, two parts of F block, one is the lanthanide series and one is the actinide series. So rare earth elements, they consist of the lanthanide series, lanthanum plus 14 elements, okay, and scandium and yttrium. Okay, so these 17 elements. So elements such as cerium, praseodymium, then neodymium and europium, gadolinium, then terbium, holmium, erbium, thulium, erbium, lutetium. So all these are rare earth elements. I hope the difference is clear. So we are focusing on lithium and its comparison with sodium. You can see here sodium, which is not a critical mineral. That is why what we are trying to do is to shift the dependence of electric batteries and electricity run components from lithium to sodium, which is a novel technology. Okay, so we'll discuss the reasons why we are going after this switch. Now, what is the problem with lithium apart from this? So first of all, we have already discussed that 60%, about 55 to 60% of the lithium reserves, they are concentrated in this lithium triangle. Okay, lithium triangle, group of three countries, Bolivia, Chile, and Argentina in South America. So 60% are concentrated here. Okay, so here these are lithium reserves, Chile, Australia, Argentina. Okay, now countries supplying the production. Okay, the countries with the maximum, who are the major producers. So Australia stands tall here. We talked about Australia. The reason why Australia was initially made part of Pax Silica and India was left out because India does not have enough reserves of lithium, and also even if it gets that technology, that processing power to produce lithium, it cannot do so. So Australia. So this is a major bottleneck. Okay. So currently, where do we stand in terms of lithium and sodium? What are the initiatives which have been taken? Now, China has already proceeded with the adoption of sodium ion batteries in its passenger vehicles. And this Chang'an Automobiles, it has established a collaboration with CATL, which is Contemporary Amperex Technology Limited Company, which is a major player in the production of lithium ion batteries, and they have already produced, they started mass producing a sodium ion electric vehicle which is 20% cheaper as compared to the normal lithium ion electric vehicles. Okay, so China, as always, it has taken the lead. Now where does India stand? So India, this Reliance Industries, some time ago, it took control of the Feradian. This is a UK based sodium ion battery manufacturer. Okay, so this company was taken over by Reliance, and India, this, what is the measure? Kabil, Khanij Videsh India Limited. So you know the acronym play of the government anyway. So this is actually a joint venture between Hindalco, Hindustan Aluminium Company, then HCL, Hindustan Copper Limited, and MECL, Mineral Exploration Company Limited. So this is now also a part of the National Commission for Critical Minerals. Okay, so this Kabil, it's a joint venture which is responsible for securing the supply chains of essential minerals and materials like aluminium and cobalt, lithium. Okay, then what else? The recent initiatives, PLI schemes for Ola Electric by the government, and chief beneficiary of about 18,100 crores for its gigawatt hour plant in Tamil Nadu. Okay. Then the target to be two and three wheelers first, because these, we are first looking at mass adoption instead of distance, or the length or the distance which a vehicle travels, rather than day to day, the mass appeal or the mass infrastructure which can be established here, and viability procedures such as the viability gap funding. Okay, so this, I hope you have understood the difference. Okay, so before we come to the interesting comparison that why sodium batteries are being focused on, what advantages do they bring over lithium batteries, and the comparisons straight by straight, we're going to understand some chemistry, some basic, the 9-10 chemistry, because this is actually interesting. No one actually discusses this in the news. So how does a cell actually work? So this battery is small. Okay, AAA, AA batteries, you understand there is a positive terminal, negative terminal, also known as anode and cathode. So I'll try to keep it as simple as possible, but it's actually interesting. So basically, this is an example of an electrochemical cell. Okay, so this is what is packed inside this cell. Okay, so we have two electrodes basically. One is the anode and one is the cathode. What is an electrode? Electrode is basically a conducting material inside an electrochemical cell, which is the site of reactions, the chemical reactions, and which helps in the motion of electrons and the positive ions throughout the cell. Okay, basic components of basic components of an electrochemical cell: anode. In case of an electrochemical cell, it is a negative electrode. In case, and this is cathode, this is the positive electrode. Only in case of electrochemical cell, the signs or the polarity changes when it is getting charged. Okay, so we are talking about this. So what happens is, we are discussing about lithium here. So in case of lithium, we'll keep it simple. So the material which is used to make the anode of the is the graphite. Okay, and it is covered by copper foil. Okay, so graphite, the element which we use to make pencils, it is not lead, it is graphite. Okay, it is an allotrope of carbon. Okay, I'll explain in brief. So this and the structure is like this. This hexagonal structure, normally carbon is a very amorphous and is disordered in structure. It does not have a particular structure. But under high temperature and under special conditions, the carbon becomes arranged in this hexagonal structure, crystalline form, okay, sort of arrangement. And here in the anode, what happens is this graphite is used and lithium ions, Li plus ions, are placed, they are packed inside this graphite. Electrons are also around this. So this is the basic idea. So what happens when a bulb is connected or any electronic appliance is connected across this anode and cathode? For example, if I take this cell and I try to connect any bulb. So this is basically this is the anode and cathode, and we are going to connect the bulb across it. So what happens is here the lithium plus, it enters the electrolyte. Electrolyte is basically a liquid type substance which consists of salts, which consists of a salt solution through which the positive ions can transfer. Basically, you have to remember this rocking chair mechanism. I'll come to it. I'll summarize everything in one go. So when it is connected, so lithium ions, they enter here, okay, and they move towards the cathode, start moving towards the cathode. And at the same time, the electrons, the negatively charged atomic particles, they start moving via the external wire to towards the cathode. And here they again combine the lithium. Here the cathode is made primarily of cobalt, and in lithium ion batteries it is surrounded by aluminum foil. Okay, so here they form a compound such as lithium cobalt oxide. So this is the basic. I'm trying to make it less complicated. Okay, so what is happening is when it is acting as a cell, that is, the cell is providing an energy, it is not getting charged, it is getting discharged. So in this case, the anode, the lithium ions from the anode, they travel into the electrolyte solution, the liquid solution, they travel towards the cathode, and the electrons, they travel here, and they both combine and they form the lithium cobalt oxide. Basically, this cathode is also made of lithium cobalt oxide, but to make things simple, I am explaining like this. Okay. Now, I was talking about the rocking chair mechanism to make it clear. Okay, so what is that? Electrons, rocking chair mechanism essentially refers to that electrons are not coming or going from outside, or they are not getting eliminated or not getting destroyed. It is simply a transfer of energy. It is simply the same electrons which were here earlier, they are going to again transfer back in the when the charging is going to take place. So when this cell is discharged, suppose, so we put it in some battery charger. If it is a rechargeable cells, not all cells are rechargeable. So now we are in the charging phase. So what happens is now this becomes the negative electrode and this becomes the positive electrode. So initially the Li plus ions, lithium ions which were here, they start moving towards here, the graphite anode. This is primarily made of aluminum plus cobalt, and electrons also, they start moving here to occupy the initial stage. Initial stage, we remember that this was the lithium ion packed inside the graphite. Okay, so this is the basic structure. So rocking chair mechanism. During the discharge phase, the lithium ions enter here, they travel towards cathode, electrons travel through the external circuit, they light up the bulb, and during the charging of the cell, rechargeable battery, the lithium ions, they move back, and electrons also move back to form the lithium in the graphite. Now, why and how lithium ions exist in the cell, why it is not lithium metal, how is lithium already lithium cobalt oxide and all that, we're not going to go into this. It will become very prolonged. So I wanted to emphasize on this. because this structure will become important in one of the cons in what is hindering the development of sodium ion batteries. This, you can see, this is the flag of DRC, Democratic Republic of Congo. Again, cobalt is an essential, it is a critical mineral. A significant proportion of the world's cobalt reserves are found in DRC. So again, this is supply chain restriction, supply chain area which is strategic, and India is vulnerable in case of that. Okay. Now, the interesting part, the comparison between sodium ion and lithium ion. Okay. So, first of all, we are going to talk about energy density. Energy density means how much energy is stored per kilogram or per unit mass. Okay. So essentially what happens is lithium, I'm not going to explain why what the chemistry is. Basically, the same amount, if we take 1 kg of lithium and 1 kg of sodium, this 1 kg will produce more energy. Okay, so it can be around 160 to 200 watt hour per kg. In case of sodium ion battery, it is around 100 to 150. Okay, so what will one of the cons here itself we have, already lithium batteries are very heavy, if you have heard. Why? Because if we compare the energy density of petrol or gasoline, it is to the tune of 12,000 watt hour per kg. Watt hour is a unit of energy, watt into time, power into time. So that is why less amount of petrol is able to run a car for long, but high it is energy, huge packs of lithium ion batteries they have to be used in cars. So this is one difference between lithium and sodium. Okay, next, lithium is lighter in weight, atomic mass is less. Okay, atomic mass, you understand, the mass of protons and neutrons. So it is different from atomic number. Atomic number is the number of protons in an atom. Atomic mass, what is used to calculate the overall mass. So it is normally 7. Here sodium has a higher atomic mass of 23. So again, if we start using sodium ion batteries, the logistic cost, the weight of batteries which will increase. But the major issue, the cost, okay, it has already been observed that lithium, this, if we use sodium ion batteries in passenger vehicles, the production cost, the battery production cost can be reduced to the tune of 30%. Okay, so this is a big positive. Okay, then moreover, we are already dependent upon imports for lithium. This sodium is the sixth most abundant element on the earth. So it is easily available. It can be obtained from sea salt and soda ash. Okay. Then currently we have already discussed around 60% of lithium reserves in the triangle, in the lithium triangle. Then over 80% of the world's battery production cycle, that processing component, is dominated by China. So this intends to counter that. Okay. What else are the differences? This flammable. You might have heard of news electric vehicles catching fire. So this is why? Because first of all, lithium is highly reactive. In chemistry terms, it is highly electropositive, or we can say, okay. Then the electrolyte used is an organic solvent. Basically, in layman terms, all the elements, all the components which are used in lithium ion batteries, they are highly prone to prone to reactions. Higher reaction produces higher heat. Heat increases further other reactions, and this cycle goes on until the battery catches fire. It is not so in case of sodium, okay? Because of differences in electrolytes, because of differences in anode and cathodes, okay? Then here, when we are mentioning about the differences in anode and cathode and cost factor, in case of lithium ion, we have already shown that copper has to be used in anode and aluminium at the cathode. In case of sodium ion batteries, aluminium can be used at both anodes and cathodes. Remember, it is a foil surrounding the graphite. Actually, electrode is out of graphite. Aluminium is much cheaper and lighter as compared to copper, and that is why it can compensate for the high weight of sodium. Plus, the anode, in this case, the cathode is comprising of cobalt, lithium cobalt oxide to be precise, which contains oxygen. And when this decomposes, it provides free oxygen, which can lead to combustion and fires. In this case, in the sodium ion battery case, there can be cathode can be made of polyanionic compounds like sodium, sodium iron phosphate, which is less reactive, and also Prussian blue analogues. So just for additional information, okay. So other concepts are there. I'm not going to go much into that. Then here, this sodium ion batteries, they are resilient in low temperatures. So in places like Ladakh, high altitudes, for applications, these sodium ion batteries are they can easily work. They operate easily without any hiccups in the high altitudes. They are resilient to low temperatures, unlike the lithium ion batteries. Then the discharging. You might have heard that lithium ion batteries should not be discharged completely. They have to maintain at least a charge of 30%. On the other hand, sodium ion battery can be discharged to 0 volts. So what benefit does it give? So example, if we are transporting a battery via trucks or other shipments or cargo. So if minimum charge is, we have to try to keep it to the minimum charge. Otherwise, there is a short circuit can take place, or any decomposition of electrodes can take place. Any mishap can happen, can take place. But this 30% minimum criteria doesn't allow it to take place. So they have to be taken as it is. So it is a fire hazard, and logistic cost, they also increase, not in the case of sodium ion battery. And then this thing is very essential. I've made this farm. Okay. So for this, I'm going to go back to the diagram again to help you understand better. Basically, I said that in lithium ion battery, we are using this graphite. Now, in a sodium ion battery, we cannot, graphite is not possible. Why? Because sodium ion is much larger in size as compared to lithium ions. So it cannot be packed neatly, closely in proper spaces between this carbon atoms, or this graphite, this between this graphite. So that is why we have to use hard carbon, or carbon which normally exists in nature. So I gave this image of agriculture. So how does it hard carbon? Agricultural waste. What is organic matter? The primary component is carbon. So those wastes can be used to make electrodes, the anode in a sodium ion battery. So what will this will also help farmers, and also the residue, the stubble burning issue, that can also be resolved. Okay. The but if we are using hard carbon at the same time, this also becomes a con or a negative aspect for sodium ion battery. Why? Because the pores in which the sodium ion batteries are arranged, they are disorderly in fashion, and the technology is not so well developed right now, so they can easily travel, they can leave this anode and travel through the to and fro the electrolyte. So that is still it is a novel technology, it is still in development. And finally, India also has the 2070 target of net zero carbon emissions. So, this sodium ion battery will also help in achieving that, along with the strategic significance reduction in imports and all these benefits. So, apart from this technology aspect, investing in Pax Silica, investing in this novel technologies of sodium ion battery is a significant geopolitical and strategic pivot that India is now standing on, and it has to take advantage at the same time to develop its hardware capacity and supply chain resilience as well. So, I hope today's lecture was enlightening for you. Till we meet again next time, Jai Hind.